Oh, this is Ron Mass. I'm a graduate student at Pittsburgh State University. This is a project for GRT 750 technology, Dr. Goris, instructor. This is an overview of the force required to stop a vehicle and the various components required. I am a ASE, Automotive Service Excellence Master Tech, and also a full member of the Society of Automotive Engineers. This presentation is not meant to be an engineering exercise nor a maintenance overview. It's simply a common sense look at automotive brakes and how the components work and some of the safety issues and maintenance issues involved. In my former job, I was an airline captain, and my second career is teaching automotive technology. And of course, I get asked questions all the time about vehicles and cars and trucks and so forth. But one of the questions I always get, because I was also a professional racer a long time ago, nationally and world rank, how fast does it go? How much horsepower does it have, and so on. No one ever asks me how quickly something will stop, and that's actually more important than the horsepower question. Well, the forces required to stop an average vehicle are easy to calculate. Um, you look at the slide, we have kinetic energy, which most people know is 1/2 the mass times the velocity squared. And then work is force times distance, distance usually indicated by the letter S. Now, all these calculations I did in metric to avoid the mass problem. If you ever worked with slugs in the English American unit, you know what I'm talking about. Mass is easy to work with. This problem is based on an average 3,400-pound car, and that's about the weight of most cars these days with one occupant. Traveling at 60 miles an hour or 97 kilometers per hour, which works out to 27 meters per second, with an average stopping distance of 100 feet or 30 meters. Now, that 100 feet is also approximately 180 feet total distance, but that 80 feet is the reaction time. So the total stopping distance is only the time that the brakes are applied. So keep that in mind. It takes approximately 80 feet to react, put on the brakes at that speed. The average sneeze is about 3 seconds. And at 60 miles an hour, which is approximately 88 feet per second, you've traveled about the length of a football field. So just imagine how far you can go when you're texting and not paying attention. Not not a lecture here, but a lot of accidents caused by cell phones and particularly texting. Rounded everything off just to make it easier, so we'll take a look at that. Okay, let's record or take a look at the force required to stop the vehicle calculation. Now, the total kinetic energy required to move the vehicle to our final velocity is T1, and T2 is 0, of course, when we come to a full stop. And we're not taking into account any accelerative factors here, just the simple equations. Newton second, force equals mass times acceleration. Once again, kinetic energy, 1/2 the mass times the velocity squared. Work, force times distance. Now, on our imaginary car, our kinetic energy, uh, 1/2 times 1540 kilogram times 27 meters per second squared. If we work it out correctly, we square the 27 times the 1540 divided by 1/2, and we come up with 560,000 joules. We could relate that to watts in the English system, but we'll leave it at joules so that we can use newtons and convert that to pounds of force. So the force required to stop is equal to the work divided by the distance. We just solve the work equation. So we get 560,000 joules divided by 100 meters, and that works out to 5,600 newtons, rather. Excuse me. So 1 newton is 0.225, or approximately 23% pounds of force. So the total force required in pounds is around 1260. Now that's 82% the weight of the car. That's a lot of force. Now, the thing is that on vehicles, most of the stopping force is from the front of the vehicle because of weight transfer. And it's approximately 60 to 70%, and with the other 30, 35% roughly in the rear of the car. So the front brakes do a lot of work. And now, if you think about that in terms of horsepower, which is a rate, it's difficult to equate force and horsepower directly. We don't need to do that, but that's a lot of thermal energy required to stop your vehicle. So your brakes need to be in really good working order in order to maintain the safety of your vehicle. Well, as you can see, the brakes do a lot of work. No pun intended. Engineering joke. The brakes work by the conversion of kinetic energy into heat or thermal energy. And newer vehicles and some racing cars, such as Formula One, which is the ultimate in high-tech racing, use kinetic energy recovery systems, or KERS, to capture the heat energy of braking and then use it to charge the batteries. Now, this can be done in a hybrid or an electrical vehicle. I get a lot of emails and literature on this weekly, and it's an rapidly advancing technology, and it's very important because it makes the vehicles more efficient. More energy that you can recover, um, the more efficient and less uh, fuel the vehicle will use. Now, of course, with a total electric vehicle, there aren't any carbon emissions, but that's always a problem, even with hybrids and certainly with full petroleum vehicles. There's two main types of brakes used in production vehicles: discs and drum brakes. Drum brakes are not as efficient as disc brakes. They've been around since the beginning of the automobile. And since around 2007, the industry began switching over to using discs. Now, why, I don't know, because discs have been around since the 30s on aircraft, and European cars have had them for years, but American car manufacturers kept using them in the rear mainly up until around 2007, and have slowly converted over. Be that as it may, drum brakes, or disc brakes rather, are still used on the back of many trucks. Most of the trucks use disc brakes in the front, hour. Now here we have a simple comparison between a disc brake on the left, one in the middle, and then drum brake on the right. A disc brake is a simple clamping device. It works off of hydraulic pressure, and you may recall that pressure is equal to force over area. So the hydraulic pressure increases and applies pressure to the pistons that you can see sort of inside of the brake caliper, which is the beige unit there. The wheel hub on the left is what holds your wheel and your lug nuts. The disc is the rotor that spins around. And quite simply, the metal pads with the lining material attached, which is the yellow, clamp down on the rotor and produce a stopping force, converting the force on the brake pads into thermal energy, which stops the vehicle. The brake pads in this type of system are easy to change. You just remove the retaining pins and usually an anti-rattle clip and pull the pads out. On the right, or the middle rather, we have another type that's different, similar than the one on the left. It doesn't have hydraulic fluid or two pistons on both sides. It's cheaper to manufacture. It works well, and most American cars that are not high performance come with this type of brake, even some of the ones that are high performance. You have one piston that pushes in on the left there, and the brake caliper moves on sliders. It's called a floating or sliding caliper. Newton's third law: every action equal opposite reaction. It's cheap. It works pretty well. Not as well as the double-sided. On the right there, not a very good picture of drum brakes, and I'll elaborate on that in the next few slides. Now this slide has a little better picture. The disc assembly on the left has 6 pistons, 3 on each side. This is off of a Mercedes AMG. It's fairly high tech. The holes are for gas ventilation from the pressure built up from the pads contacting the rotor. Temperatures get quite high, and then ventilation ribs in the middle, and they can also slot these to help move the dust away from the rotor surface of the brake pad. The picture in the middle is a sliding caliper. You notice that the piston only has hydraulic fluid on one side, and they don't show the slide, but the caliper itself moves, Newton's third law, and applies the clamping force to the rotor. On the right, you can see a typical drum brake. At the top, it has a wheel cylinder, what they call a wheel cylinder. It's actually just a hollow tube with two pistons, one facing in each direction. And when you apply the brakes, hydraulic fluid under pressure moves the pistons out and pushes each of the drum shoes out toward the drum. And that applies the brakes. As I mentioned, there are two types of drum brakes, sliding, or rather, I'm on drum brakes here. Servo and non-servo, that's the second sentence there. The drum brake shown below is a servo brake. I'll explain that more in the next slide. And the two types of disc brakes, which I talked about earlier, are sliding and or floating caliper and double-sided. And the brake below is a servo type brake. This type of drum brake shown here is the non-servo type. And the reason it's called the non-servo is because if you notice at the bottom of the shoes, the shoe anchor, there are two pins there. So when the shoes move out towards the drum, they pivot like a horseshoe. And the bottom does not move, it just pivots. And on the right is a typical drum. It's a smooth finish. And the brake shoes press out against the drum, and that's what stops the vehicle. Now, both brake rotors and drums have minimum diameters, or rather minimum thickness and maximum diameters. The minimum thickness is the rotor, the maximum diameter is the drum. Both of these are stamped or cast into the surface of the component. It's a DOT federal law that when these are turned by your brake repair place, reconditioned, they cannot exceed that number. The component has to be discarded and new ones put in place. The trend these days has been toward just replacing them because when they come from the factory, they're ground, not cut on a lathe. The surface finish is much better, and the component cost has dropped considerably. I would highly recommend when you need to replace your brake drums or discs, just put new ones on. They'll last longer. This diagram is a typical automotive braking system. It's very simplistic. It's non-ABS or anti-lock brakes, which most vehicles are these days. And it just shows you the front brake disc and the rear brake drums, and then the master cylinder with the brake pedal and the brake lines. The little valve in the middle there is the proportioning and metering valve, which meters pressure to the drum brakes at a different rate in order to prevent lockup and to prevent the vehicle from nosediving under braking. You'll notice that the brake pedal, that's where the force is applied, and then a small piston, force equals pressure over area, creates the pressure consistently throughout the system, Pascal's law, and then that pressure is converted into force again, either through the wheel cylinder on the drum brake or the pistons on the disc brake. So it's a force multiplier. Very effective. Early cars had cables or metal rods to do that. Early wagons, they used a piece of leather and a curved pad to stop the wagon. So not much has changed except the way we do it. But that's a typical system, but it's a non-ABS system and a bit simplistic. Now this slide is a good illustration of drum and brake shoes and brake pads on the right. The brake drum located on the left here. You can clearly see the curved shoes. You notice that the shoe in the back right of that plate is bigger than the front, and that's due to the servo effect. The rear shoe wears quicker, and because of a servoing action or self-energizing. A bit more complicated than that, but the long and the short of it is you have to make the rear pad longer, or it would wear out quicker. And the drum is on the right with the wheel studs where the rim goes. And on the right, we just have the brake pads, which you can tell are very simple compared to the brake shoes. So in closing, this is just a basic overview, not intended to be an engineering example or explanation. But here's some keys to maintaining your brakes properly. Always use the recommended brake fluid. And the easiest place to find this is on the master cylinder cap. Now under the cap is a rubber diaphragm. You want to make sure that that's kept clean. There is air on top of that. Otherwise, the system would pull a vacuum. But that air doesn't get into the system as long as your master cylinder is full. Normally, what's recommended is what they call DOT 3 or 4, super DOT 4. You never use DOT 5, silicone-based fluid, in a vehicle with anti-lock brakes or ABS. Most fluid is usually either 3 or 4 or super DOT 4. Super DOT 4 is comparable or can be used with the above the other 2, 3, and 4. But silicone fluid is not recommended for ABS brakes, and no vehicle that I know of other than Harley-Davidson motorcycles use it on a few of their bikes without anti-lock brakes. But that's about it. Now, brake pads used with disc have little tabs that scrape when your brake pads get low. When you hear that, you need to have your brakes checked. It's normal, they won't damage your rotors, and brake drums in the back, the shoes will scrape as well. And that's a little more serious because that scraping sound you hear is the metal where the shoe is making contact with the drum. And you need to have those checked. Brake fluid is an alcohol-based fluid. Even if it's synthetic, it's hydroscopic. In other words, it absorbs water. Everything gets water in it. Water's everywhere, even out in the desert. And it gets in. And eventually you will get water in your brake system, even if it's not open. And most manufacturers recommend changing your brake fluid about every 60,000 miles. Also, heat generated at the rotor will absorb air around the caliper pistons, and air will get into the system, and all air contains water. So changing it about every 60,000 miles will keep your brake system working well. And the fluid should be clear, somewhat amber. Dark or muddy looking fluid is a definite indication of contamination and air in the system. And the system should be flush. Proper way to change your brake fluid is with a pressure bleeder, and most shops have that. A nominal price on that shouldn't run more than $75 to $100. Any more than that, and they're overcharging, in my opinion. And remember, fluids are not compressible unless they contain air. And so that's just an overview. You should keep your brakes in good working order because, as we saw earlier in the slide, it takes a lot of force to bring your vehicle to a stop. And it's every bit as important as your engine or your transmission, if not more so. So thanks for listening. This is not my area of expertise. I am an instructor, but this is quite frankly my first attempt at this, and I appreciate your patience and your attention. Thank you. This is a picture of me in 1979 on a Yamaha TZ750. The top speed on this was about 200 miles an hour at Daytona on the banking. And as a disclaimer, all of the material presented in this presentation is public domain. None of it's copyrighted. It's been around for years. And I looked at that carefully. And thanks again.